Okay, so for the last talk of the morning session, we are very happy to have Tom Taylor, who will take us into the deep IR.
Thank you, Andra. It's a great pleasure to be here, and thank you for organizing that. So we will dive deep into infrared. And the work I will present was done in collaboration with Ben Zhu, who's now in Edinburgh. And it's one paper and also I'll talk about work in progress. Okay, let me start from a really big number. So 10 to the power 24 is essentially the ratio of cosmological Hubble length to the distances that I probed, let's say, at Large Hadron Collider. So it's a huge number. And for the purpose of my talk, Hubble length will be infrared, while we just live in a very, very high ultraviolet. I'm not even mentioning this extra 15 orders of magnitude that would take us to the Planck scale. There's another story. So another way of saying that is that we live in a world which has some positive curvature, but very small. And the first question that you want to ask, how does infrared, decouples from ultraviolet, which we live in, so that, let's say, when talking about particle physics, we can use just standard quantum field theory books. Actually, I call it, you see here, something which is like Appelquist 1 over inverse Appelquist-Karatson theorem, because there's a similar problem which we addressed long ago, which is that, as now, and we talk about physics here at, let's say, at accelerated physics, we talk about this super high energies, like Planckian energy and so on. The question is, of course, how this ultraviolet physics decouples, yes? And there's a famous theorem, which is called Appelquist-Karatson, which actually tells you that while we compute, for example, beta functions, then we can use, let's say, if we can use just to compute the observables and quantum field theory, all what we really need to use is particle spectrum at the energies that you can see. Okay? So that's the first thing. Then there's another thing, which as you will see, there's lots of interesting stuff happening in deep infrared. I mean, when you have processes which now will involve like very, very, very low energies, or another where it's occurring at very, very large distances. So we want to dive deep infrared, but we need to learn swimming first. And the framework for addressing this type of questions is to construct the S metrics in curved spacetime. There are a couple of other motivations which are at the end mentioned in his talk. And the one is that we would like to have some simple formulas for scattering amplitudes in curved spacetime, at least in maximally symmetric situations, like ADS or DS. And just hoping that these formulas are equally simple as some, well-known formulas in quantum field theory. Okay? Another motivation is that this discovery of the deformation of W infinity algebras by the cosmological constant, and for that exactly, you would like to proceed in the same way as in asymptotically flat spacetime. You would like to actually obtain this algebra from scattering amplitudes, from soft theorems. Okay, so these are other motivations for that. All right, so once again, so in the first approximation, our space-time is flat. Okay, we have Poincare symmetry with 10 generators, and we do physics by inertial observers, who measure some observables. And when you read the quantum field theory textbook, nobody really tells you which observables you pick, because all inertial observers are equivalent due to Poincare symmetry. Now, in the first approximation, we have some small curvature, and we would like to compute some observables. Okay? So now, then of course you ask observables, you compute observables, who's going to observe them? Okay. So again, if we have, in general case of constant curvature is very complicated because you have observers which are not equivalent. Okay, so, and you don't want to computation for each observer one at a time. So there is, however, there is the situation in which you can have really full control over observers, okay, and you don't worry who's measuring observables, because all observers are equivalent, is the case of maximal symmetry with also 10 generators, in which case all observers are also equivalent. So this is the case of so-called global de Sitter spacetime, and the best way, you know very well, to visualize it is to start from 5-dimensional Minkowski space and impose this hyperbolic constraint. And then what you get, this hyperbolic surface with spatial sections being 3 spheres. Okay? And then this constraint, of course, is symmetric under 5-dimensional Lorentz transformations. So the symmetry of this, the isometry of this spacetime is SO14, which is generated by the Lorentz generators of this embedding 5-dimensional Minkowski space. So the sitter is a topologically like a sphere, 3-dimensional sphere, times real line of time. And anyway, the metrics which we are going to use, okay, is this so-called global or conformal metrics, in which it's just a flat metric with this time-dependent conformal factor. And then, okay, in this parameterization, I'm using the time which runs over just from minus pi half to plus pi half. Okay. And then observers, the next thing is to talk about observers. Observers just idle on time like geodesics. Okay, so the geodesics and the sitter spacetimes are very simple. They are as simple as geodesics on a sphere, because the sitter is essentially like the rotator, okay, you complexify time. So all what you do to construct time-like geodesics, you take you start from the spacetime, from the sitter spacetime, and then you take planes which go through the center here, and actually geodesic lines are the lines which are curved by this plane intersecting with the hyperboloid. Okay, and from that also you see that all geodesics are related by Lorentz transformations, because all you can do is just rotate this plane in all possible directions. Okay, so then all observers, all are equivalent. There is another thing which I should point out, which is that for each if you take such a plane, we will have one geodesic, one intersection, another intersection, and they are related essentially by reflection symmetry, x goes to minus x in embedding Minkowski space. Okay? So there's always a mirror observer. Okay? Actually, as I mentioned before, all observers, all these pairs of geodesics can be are equivalent to any other two. So the most convenient one is to take just take this geodesic which goes just up, let's say, an x0, x1 plane. Okay, and when I compute something in this frame, and I use and by using manifestly this is the symmetry, I'm guaranteed that will hold for all observers. Okay? That's very important. I won't need meta observers. Okay. All right. Now, also from here, you see that that these two, actually, the one thing which I'll also point out, then on a given geodesic and its mirror can never communicate with each other. Yes, as you can see from here. Okay. So let's start developing quantum field theory in this de Sitter background. The rule number one, that in the deep ultraviolet, okay, which I will define in a minute, physics or quantum field theory in de Sitter spacetime should be the same as physics in Minkowski spacetime. Okay? Now, so how to do it? Well, you just, to realize it, okay, in practice, what you do, look at the wave equation. Okay, I will consider it a scalar field. And you just write the wave equation. And by the way, this four-dimensional Laplacian now will have also part which is Laplacian on three-dimensional sphere. So it's, you do the usual thing. Then you expand solutions in the harmonics, in this case, so-called hyperspherical harmonics, because these are SO4 harmonics, which are, that's very well known, they are labeled by three integers. Essentially, one of them is just SO2, another SO3 angular momentum, another SO4 angular momentum. Okay? And they range, and these are all integers, and they range, of course, the M range. They have the usual range, which is written here. Okay? Now, there's one thing which I also should mention, which will come later in, that also these numbers, they label representations of SO14. So there's there is a one-to-one correspondence between the states belonging to the representations of the de Sitter group, yes, and spherical harmonics and hyperspherical harmonics. Okay, so what is ultraviolet limit? Ultraviolet limit is the limit in which there are now these hyperspherical harmonics are oscillating like crazy, okay, which means that you have to go to very high angular momenta, okay? Then you'll be probing short distances, okay? Actually, there's an equivalent way of doing it. There's another way of describing it in more like particle physics terms. Actually, if you have an observer, let's say, on the North Pole, okay, so he or she or it may want to consider just plane waves, okay? Then you can actually expand you can construct plane waves in the neighborhood observer by taking superposition of those harmonics, yes? Which is rather obvious because one of the radial direction on the plane is just the direction of one of polar angles on the sphere, okay? And then you see that, and this is that actually the momentum, okay, the wave vector of this plane wave is just given by this SO4 angular momentum. So the limit of large SO4 angular momentum is the limit of the large linear momentum on a tangent plane, okay? These formulas are very well known in case of regular harmonics, but they exist also for hyperspherical harmonics. Okay? Actually, there's a nice, very book written by Avery about hyperspherical harmonics. So now, what do you want to do? I said that in this case, you want physics to be like in Minkowski space. That we want to have the wave functions for those high angular momentum wave functions. We want the time-dependent part to oscillate with positive frequencies. This will identify the wave functions of particles. Then, of course, complex conjugate will be wave functions of antiparticles. Okay? And yes, and that requirement, although the initial equation is, of course, second-order differential equation, yes, for the wave equation, that picks up unique one solution, okay, which is written here. It's essentially a Legendre polynomial, whose Legendre function, it's called associated Legendre function, it's not polynomial, okay? It's associated Legendre function in which the time dependence on time is through like complexified time on Minkowski space. Okay? And the order, okay, which is the upper index, okay, is related to, order is related to this angular momentum, and then the degree is related to actually the mass. Okay? Actually, this okay, you're familiar very well, I'm sure they're familiar with relation of polynomials. In this case, this is exactly the same thing, that if you started instead from the sitter, you started for four-dimensional sphere, and you solve Laplace equation of a sphere, and then cleverly analytically continued. Okay, so it will be hyper spherical harmonic of SO5. Okay, but since we have a non-compact time, so they finality continue, and in this way you obtain unique solution up to, of course, a constant. And these solutions were discussed, okay, starting from 1960s by Chegetagerev, and then later also discussed at length in a really very important paper by Emil Motola. Okay, so yeah, and then again, this, by the way, they are labeled by this parameter mu, which is related to the mass, to this relation. And for the purpose of this talk, we will assume that this this parameter is real, assuming simply, well, as the end of the day, you will see that this parameter mu, actually, as you see it here, is related to the mass, and so we are taking large mass. Yes, certainly masses of even like electron mass is 10 to 32, and the units of Hubble mass that you obtain in an obvious way, yes, which is very light. Okay, so we have now these solutions. And by the way, these solutions are often called Bunch-Davies solutions because they're obtained by analytic continuation from a sphere. And then once you quantize the field and decompose it into positive energy, positive to particles and antiparticles, creation and annihilation operators, you have a unique vacuum. And this vacuum is something which goes in the literature under Bunch-Davies vacuum, or unique vacuum, Euclidean vacuum. It's the only vacuum in the sitter that makes sense. Okay, so alpha, for example, which had a property that we can connect to in the flat limit, okay, for processes which is equivalent for processes which occur at very short distances, can make connection with Minkowski space. All right, so we have set up at least 3 fields, yes? By the way, then the wave functions, I already mentioned that these wave functions describe, you can think about them as describing states which belong to representation of the sitter group. And then when you take a large mass, there's unique representation, at least for spin 0, which is called the principal series. Okay, so then, yeah. So these are wave functions of states with definite angular momentum. Okay, so the next thing, of course, you want to develop quantum field theory, we need a time evolution operator, which is the Hamiltonian, right? Because then we can start evolving states and scattered states, we can interact and scatter. Now, the Hamiltonian in the sitter space is the boost generator. And we can associate it with the Killing vector of the boosts. This is not a standard thing because usually you associate Hamiltonian with the Killing vectors which are globally time-like. This Killing vector is not a time-like, but is, as you will see, it's good always close to observer's trajectory. We really don't care what's happening anywhere else. We just are interested in the neighborhood observer. Now, there are 2 ways of arguing that this is the boost. Okay, one is there is a beautiful paper, like 10 years ago, by Cacciatore and others, in which they consider the following problem: you'd have an observer, okay, who's again just moving, let's say in this case, like this observer in 0-1 plane, just idling, and then you have a particle which is following some trajectory, and so the observer sits here and measure particle's energy. Now, each geodesic is characterized, has conserved quantum numbers, and one-to-one correspondence with the group generators. Okay? So actually, if you see what the quantity, which is the energy, is simply the product of those conserved quantities of that form. And actually, this is, you can show, that is the quantity which is, for particles geodesic, it is the quantity which is net charge of time translation variance of this particle propagating the Sitter background. Okay? So now, and then in addition, they show that if you take a flat limit, you'll get the usual, well, sort of E equal mc squared. Okay? So this is really the formula for the energy. So when we do quantization, then of course we keep classical observer, yes, and we quantize, we replace particles energy by the operator, by the quantum operator. Okay, and you see that when you pick, for example, a 0-1 plane here, you will see that's a 0-1. Okay? There's another way, which is sort of even more intuitive, to argue the same thing. If you look here at if you look at, again, this 2 geodesic, which is in a 0-1 plane, then of course it boosts in direction 1, then the observer will be time evolving, moving in the upward in direction, it'll be evolving in time. And now on the other side, his mirror will be moving actually in the opposite direction. Okay? But what is important for me, that the time evolution of the operator is regenerated by boosts. Okay? So, and then we can make it more precise than by associating with the corresponding Killing vector, and you get expression for the Hamiltonian, which is very similar what you have in Minkowski space, up to some factors which depends on geometry. Okay, but I won't. Okay. Then what you do next? Now we had so we agree that we have a Hamiltonian, okay, which is given by this formula which I had before, which I wrote here. Okay, what you do next? We construct the S matrix by following step by step the same procedure which is described in many textbooks. The one which I particularly like is Sidney Coleman's notes. Okay, so what you do, you start from and observe as proper time in past, infinite past, and then there you start with some state which belongs to a given representation of the Sitter group. Okay, in Poincaré you would be considering, for example, scattering of states with definite momentum. Here we are considering scattering of states with definite angular momentum. Okay, and then again, so you evolve it and then the state you evolve them to far future. And so essentially you proceed step by step by using this Hamiltonian, this peculiar Hamiltonian, okay, which looks different than in quantum, that what you see in quantum field theory book. And you end up with a formula, which is exactly you find in Coleman's notes, in Coleman's lectures, which is called the Dyson formula for the S matrix. So this formula is essentially operator formulation of quantum field theory. Actually, a similar attempt of constructing S matrix. There's only one attempt in the past, which it is due to Marov, Srednicki, and one other author. but they consider LSZ formalism. So it is very difficult, the two approaches. This approach is very intuitive. You just construct the S matrix by using what you call operator approach, and you have this formula. And it's really Dyson's formula. The only difference, obvious difference that you have to include is there is this factor which makes it coordinate invariant, coordinate reparameterization invariant. Okay? By the way, it is, the point is not this S matrix element is derived by using from Hamiltonian, which is the boost. And then, of course, when you have here you have in the Hamiltonian you have interaction part, and then this interaction part that the only thing that enters in this time evolution operator. First of all, we want to have non-trivial scattering.
Is this S matrix going to compute the same observables as cosmological correlators? Or?
Yes. So that you will see how they connect. Already I told you that from those, if I want to have a scatter plane waves, you insist on them, I can make superposition of those hyperspherical harmonics, which in the observer's neighborhood, which will look like a plane wave. Yeah, and then of course they go, and then you will see that if, of course, that's one of things that I will have to, that I argue here. Then this limit, of course, the amplitudes will become the amplitudes of flat space-time.
Okay.
Yeah, so that's the whole point. Yeah, and then once again, what I'm scattering here are the states which belong to the Sitter group representations. But again, I can go to other bases. And okay, I will talk about later. All right, so that means the conclusion is then that the Feynman rules in the Sitter spacetime are exactly the same as Feynman rules that you get from here, from Dyson formula. Well, in position space. Yes, in position space. So, for example, if you have compute somehow, we have internal lines which have, well, we have a lambda phi cube theory, for example, and you have this type of diagram when these propagators connect further. All what you have to do is you perform these integrations over, well, you have to integrate over the interaction point. Yes. What is nice in Minkowski spacetime that we have a momentum representation, and actually these propagators have very simple form, and this computation is completely trivial. For example, in phi cube theory, all what you get here is just the coupling for, like, if you have like a three-particle amplitude in lambda phi cube theory, you get a coupling constant times the delta function that ensures for momentum conservation. So you see that, and if you did it again for 3 points here in the Sitter, you would get essentially, you would have to integrate over the interaction point, and then you will be integrating, essentially what you will be integrating over, you will be computing overlap of hyperspherical harmonics. So that explains essentially that, that tells you that computations of scattering amplitude at Sitter spacetime, okay, it depends how you think it's complicated or simple. Okay, if you know how to handle hyperspherical harmonics, and you're good in 3J, 12J, and actually even more symbols because they essentially are doing overlaps here of SO5 harmonics, then okay, the amplitudes will be given by those overlaps and can be expressed in terms of this high J symbols. But this is, so in other words, to develop, sort of, if I want to address this question that I asked at the very beginning, the mathematics of the scattering amplitudes is the mathematics of angular momentum, okay? So if you want to write a very compact formula, okay, you can do it. It'll be very compact. It won't be just a lambda for lambda phi cube, but it will be somehow multi-J symbol. All right? Again, if you are comfortable with it, that's fine. If you don't, you have to, if you want to do some very concrete computations, then you have to go step by step. Anyway, that's the first point. Second point, that also, since I told you that the Feynmans are the same, that means that the Feynman propagator is given by the usual formula. What you do, you take all wave functions, yes, you sum over all modes, and you sum over all them, you take the time ordered product. Okay? And you get the Feynman propagator. Now you know that the Minkowski spacetime, that is a function of the invariant distance between the 2 points, and has this beautiful momentum representation, okay, which you can use then to do computations. And actually also, if you insist going into position space, that's not a pleasant exercise, because even in a scalar field theory, the propagator are some complicated, Bessel functions, yes? So it's really, you can appreciate here how momentum representation and, Feynman rules, how simple they are, okay? In position space, this would be very complicated, because these are essentially Hankel and modified Bessel functions, which are even for a free propagator. All right. Okay, so that takes me to the propagator in the Sitter spacetime. I want to have this propagator because I want to consider now exchanges of particles. I want to consider a process in which have particles which are scattering in ultraviolet, but also I want to discuss processes infrared, and I have some soft particles being exchanged, yes, or emitted, right? So to that end, well, I have to construct the propagator. Now, there are two ways of doing it. One is exactly like here, perform this sum. This can be attempted, then it uses so-called addition formulas for hyperspherical harmonics, but it's really, really very, very hard, although I will show you explicit formula. Another thing is you just solve wave equation for the propagator. And again, this equation is, like the original wave equation is not too complicated. Again, it's going to be reduced to Legendre equation. And then, again, it will have two solutions. And then in the literature, it's already known since Motola and even before by previous papers, that by requiring that the line singularity is the same as Minkowski space, picks one solution, which is exactly the Bunch-Davis propagator. This condition, I don't know for what reason, maybe there's some French people here, it's called Hadamard condition. And I don't know why it's called after Hadamard. Okay. Anyway, but we have another way. There's another way of reaching the same conclusion, which is going straight. You can do the following thing. You can go straight into ultraviolet by taking very heavy particles, which have very small frequencies. Yes, and then you can show that if you take limit mass to limit and go to infinity, then actually the Bunch-Davis propagator reduces to the propagator in Minkowski space. Exactly, then these Legendre polynomials become Hankel and modified Bessel. Okay, and that is only was possible to this type of analysis became only possible in the last couple of years. There are papers which discuss asymptotic of Bessel functions, which are very recent paper by Dunster and others. Anyway, if you go to infinite mass, the Bunch-Davis propagator becomes exactly the propagator in flat space-time. Now, you may wonder also, now to make this, but this is still in position space, so it's not a good framework to address emission of soft particles or like virtual exchanges in which you could sit on the pole of the propagator, for example, and you see singularity. Yes. So the question is, to discuss those type of problems, you need to discuss those type of problems. You need to have something which looks like momentum representation of the propagator. And actually, this is possible. This is possible because, and this is, again, the propagator will be essentially, the propagator it will be exactly the sum over all hyperspherical harmonics, yes? But now including this time-dependent part, this time dependence, which is this Legendre function, you can use integral representation of those Legendre function to arrive to something which looks very close what you see in quantum field theory books in Minkowski space. Okay, you can write it, well, here, of course, the spatial part, you have some of these SO4 harmonics, and then this is the part which involves this time dependence. By using those integral formulas, can be expressed as integral of the type. It looks exactly like integral over energy part of the propagator. But now, and with, again, you have to use I epsilon prescription. Well, it's a generalized some prefactor here, but the point is there's an integral here of energies. But what usually here would be square of the spatial momentum plus m square is replaced by these two replaced by parameters over which you have to integrate. Okay, with some weight which is written here. You can write it explicitly. Okay, so there's no, like, it's not, in other words, in flat space-time, okay, you have a dk and you have a d3k, okay, but that part here, so now instead of this integrating over y, you just sum over them. And then the spatial part is simply it should be normal in the flat space-time. In our case, this is not fixed, but it is a continuous variable that you integrate over. One way of thinking about it is like integrating over mass, but that's not the way. You will see that I will explain it in more detail now. By the way, there's one very important thing. That if you go now, let's stick to this high energy part of the propagator, in which you are summing over high hyperspherical harmonics. Then actually, you can replace the sum by integral over the momenta in the same way as, in other words, you can go to the basis, momentum basis, and replace the summation of angular momenta by integration over 3 momenta. So that part in the ultraviolet looks like this part of the propagator. Here you have a normal e2i k x1 minus x2. Yes? So that's what you have, and now it's L here. So you see that the large angular momentum part can be written as integral over the momenta of the usual plane waves. Okay? Right? But it's in the sector, in this ultraviolet sector. And so that takes care of that. Then also that in the limit of large L, you can perform this integration over these two continuous variables by using saddle point method, and you see that saddle is exactly at the value of this combination of two variables that produces what you expect in the denominator of the Feynman propagator. So what you see here is Feynman propagator in Minkowski space in momentum representation. And this, but again, as I mentioned before, this is when you consider this is the ultraviolet part of the propagator. Yes, when you have a lower angular momentum flowing to the propagator, then of course this is where you perform this integration. Okay. So now, so once again, here again in ultraviolet. You get in the ultraviolet, you get what you expect, but what is interesting, actually, more interesting, if you go to infrared and look into the propagator when you have these low angular momentum modes which are propagating. Okay? And then what you find, since this variable is continuous, then you will always have some saddle points and so on and so on. But you will never, for example, if you have a process in which you chose kinematics in such a way that the intermediate particle would go on shell and produce singularity, there won't be such a singularity. Actually, the result will be finite and will have little imaginary part. This is what it exactly is, Breit-Wigner propagator. The reason why the propagator in the infrared look like a Breit-Wigner propagator is means that telling you that those particles actually are not stable because there are no, unless you have some quantum number, okay, which would protect decays of those scalars, there is no energy momentum conservation, so everything goes, so these particles are actually not stable. Okay? So then, but that means that there are no on-shell poles, there are no infrared singularities, and these propagators are of the type of a Breit-Wigner. So that is how this is how de Sitter propagators look in deep infrared. Okay, so I can conclude essentially that, well, the deep infrared in de Sitter is very different from Minkowski, although, again, in the ultraviolet, as expected.
Tom?
Yes?
Here. I'm down here.
Yes.
Okay. Just to understand your point, so you're saying that because of, even in the massless case, because of the L squared, the IR singularity is avoided?
Yeah, essentially our integrating is washed out. So you have no, you will not sit, you will not get a pole. You have some integrals which will always finite. There won't be singularities in the strict sense that you have a, like in Minkowski space, you have a soft particle, then you send the intermediate propagator on shell, and then it blows up, yes? Yeah. And that is the what defines infrared singularity. Here you won't. You won't have, because the propagator will be, there will be continuous integration over the momenta, okay? And the singularity will be absent.
So this is because the L integral is over a compact 3-sphere or something, you're saying?
Yeah, that's one way. Yeah, maybe that's one way of thinking about it. Yeah, but I think about it in terms of simply of instability of those particles. Okay, because that type of phenomenon occurs in quantum field theory. For example, the propagator of Z0 particle. Okay, you will never go on shell, but you have that peak.
Oh.
Ah, yes.
Okay.
So that's what this peak is, because Z0, for example, is unstable, so you cannot go on shell. And then, in addition, you have a width which is related to the lifetime of the particle. Oh, so the same thing is happening here. Those particles are not stable, simply. Unless you find some symmetry.
What's the lifetime, what's the analog of the lifetime here? The angular momentum value?
Huh?
What's the analog of the lifetime here?
Well, the lifetime, because they will live forever. Again, anything which is long is Hubble length.
Okay.
Okay. So that is the scales which you have in the problem. But I'm saying this is what I call deep infrared. Yes, of the length scales which probe entire universe. Okay. But the point is that in principle, you can develop quantum field theory that will then, and then again, those amplitudes, you can compute those amplitudes. They will not be as simple that, as I mentioned before, for example, for phi cube theory, it will not just be the coupling constant, but with some multi-J symbol. Okay? So from that point of view, again, I hope that somebody will sit on that and that would motivate somebody to develop a really good mathematical theory of those scattering amplitudes. But that requires the dealing with the multi-J symbols. Okay? All right. So, another way, again, similar to saying that somehow here this curvature acts like sort of infrared cutoff, yes? Okay, which is again we expect. Yes, universe is finite. Okay, so we cannot go over infinite distances. You have a finite size. Okay, but it also tells you from that what I told you about this infrared effect that you need a new framework for soft theorems. It's not just that you can, and in the new framework for soft theorems, you cannot just say that you have a soft particles, okay, and then you sit on a pole and things like that. You need something which would replace that formalism, and that hopefully by using this formalism, yes, we'll be able to say something about W and so on. Yes, W. Yes.
So, I mean, I think there, even in Minkowski. So the traditional way of understanding of soft theorems in Minkowski would be in a power in the energy. But that is actually a very ambiguous thing to do because of the problem that if you start changing the energy of an external particle, you violate momentum conservation. So it's a very difficult limited to define, and in order to see that these theorems organized into W algebras and S algebras, one really had to go to conformally soft, which is not the same thing as soft, right? The boost weight is becoming small rather than the energy. And that concept, I think, goes over to de Sitter space in the same way that I just talked about this morning goes over to anti-de Sitter space. So maybe that would...
Yeah, maybe that would be...
I'm proposing that's what the framework would be.
But that would be very interesting to do because, again, one thing which was, again, it was also puzzling you, why this lambda extension, you cannot get it from amplitudes, yes?
You can't, right, so, right, you can't have a soft particle in ADS, but the energy in Minkowski space doesn't map to the energy in anti-de Sitter space. It maps to some other thing. And anyway, we didn't really want the energy in Minkowski space. Of time translations, we wanted the boost energy. That was the one that, that's the thing that organizes the S algebra and the W algebra and fits in nicely.
Because
so one would hope that would be how you would think about it in de Sitter space too.
Yeah.
That would be
actually that somehow this is essentially what you're doing. The reasoning that I followed in some way because I ran out when deriving this infinite. The first thing that we tried to do is to look into papers of Alday for scattering and lambda corrections to scattering processes in ADS.
Yeah.
That doesn't work.
Right.
It simply doesn't work. There are no singularities that you need in order to have soft theorems of that type that you need to reproduce W algebra.
Right, because the time in ADS is not part of the SO31.
Yeah. All right, I think that concludes what I wanted to say, and thank you.
Yes, when you say that the propagators look like the resonances, like the Z, right? Now, resonances in Minkowski space are unstable, they decay into something else that is stable, right, eventually.
Yeah.
And what happens here instead?
There's no energy conservation, everything goes. There's no energy. Why they're not decaying, why Z0 is, if you have a process, like for example, you have one particle with mass m, if you have a lambda phi cube coupling, could decay into two particles with mass m. Because that the only, so there are many processes which are allowed at the level of Feynman diagrams, okay? But they are protected, decays are protected by energy conservation. Yes?
Yes. Maybe one other question is, you are computing evolution or scattering from global time, from early global time?
Observer's proper time. Mm-hmm. So that is crucial thing here. I have no global Hamiltonian, no nothing. The Hamiltonian comes with the killing vector, which is actually only time-like in the observer's neighborhood. On the other side, actually, it's interesting, runs in the opposite direction, but it's another story.
So like the way that I was intuitively understanding this is that in the deep UV for de Sitter, like it's very small distance scales, so it's not sensitive to the overall curvature. Does that mean then that like your results would also hold in ADS, where deep in the UV, the propagators should also be very similar to that of Minkowski?
You know, with ADS, I have a problem with that. For me, the sitter is much simpler. I can talk observers which are moving properly in time. They are moving forward at the proper time, and so on and so on. And that's one thing. Another thing that I need, the crucial element here is the sitter invariance. I'm global. With a global ADS, to even think about scattering processes is just ambiguous, yes? But the maximal symmetry is absolutely crucial, because otherwise I would be, essentially that's, when you do any computation, you have to think, you compute observables, you have to think who is observing those observables. Yes?
Do you really need maximal?
Yes,
Symmetry?
maximal 10.
Or symmetry that would foliate appropriately the space would be enough or not?
No.
When the orbits become dense.
For example, there is a similar, again, I mentioned work by Marolf and so on, which the only work which does global. There's a series of work by Pimentel and others, where you do Poincaré patch. And then you can get those, you can get to Poincaré patch. Again, there are two limits. There's a limit which goes straight to Minkowski, okay? But there's an intermediate limit in which you go local, and actually you end up on, essentially, you can think the physics becomes the same as a Poincaré patch, which does not have a global de Sitter invariance. Okay, it's just local de Sitter invariance. So yeah, so this is absolutely crucial, because then, for example, when you take these cosmological raters and so on, then you have to say who's measuring that. Yeah. Okay, that's the obvious problem.
A naive question about comparing scattering in flat space versus de Sitter. In flat space, what we usually see is that the thing that is observed are incoming states and outgoing states. And here the observation seems to be going on right in the middle of scattering.
No, he has a history. So in other words, the observer has some states. You think about that in the past. There were some states which look like these angular momentum states, and the future then. So it is, it's not like, so it's a local, so when there's a local computation, but however the states are evolve in time. That's Schrödinger picture.
I see.
Yeah.
My main question was about the outgoing states. With respect to the observer, after some point, the outgoing particles, wouldn't they look like they're merging into some thermal background? Because from the observer's point of view, you have...
There is amplitude to describe the observer who is sitting here and computing, and computing scattering of the particles coming in and coming out. The same thing as at LHC. Okay, you don't worry about at LHC. Actually, the protons are coming from just hydrogen bottle and Marron, and you really don't care. Okay, and you use, and everything works. Okay, so it's local. So measurements are local. And then this computation, they use some extent global properties, but it just, you always think about it in terms of observer's history. Yeah.
You said before that you're computing the same thing as cosmological correlators, but what is the relation?
Yeah,
because
the
those
relation
are
is that the
and
cosmological correlators are somehow trivial limit of those correlators.
What?
Are just simple limits of those correlators. In other words, Poincaré, if you consider some scattering processes, the propagator, for example, essentially, in terms of special functions, you start from associated Legendre, and in those limits, you go to Bessel's. There are these limits of special limits of large order or large degree Legendres are given by, as explained very well in those papers by Dunster, in terms of Bessel functions. So the correlators on Poincaré are Bessel functions, which is like halfway towards, like halfway between global de Sitter and Minkowski. Yeah, so they are related.
But for the cosmological correlators, there's no problem in taking like low energy limits.
They don't?
Right? No?
There's
like low, you can, what you were talking about is sort of gives a good gives a picture for a formalism for high energy scattering. While cosmological correlates, you can also take low energy limits. So.
Yeah, but they have a different, yeah, exactly, but they have different limits because again, and then again, you have to be careful what you are comparing because you do not have a global invariance there, okay? So there's one guy who's sitting there from the Big Bang and, yeah, but it's not that just you can trust, there's no simple answer what happens if you take another geodesy.
Continuing with Temple's thought, like,
Yeah.
if you are sending mass to infinity, then can we not think about, like, naively that the particles are propagating very slowly, so they are, like, we are basically sending radius to infinity, so they are not sensitive to the curvature. So that's why we are going to Minkowski space, like, in
Yeah.
UV region.
But,
So I can think of that in ADS too, right?
Oh, I see. Okay, all right. Okay, the point is that it's not just the singularity that you get, which is this 1 over the light cone singularity, 1 over x squared. That was known that was known since Mottola. Okay, and everybody used it to pin down to select Bunch-Davis. But here the point is that you take the expression for the propagator, and then you take the limit of infinite mass in an exact propagator in flat spacetime, including the Hankel. So in a space part, you get K-Bessel. In the time-like part, you get the Hankel. The usual stuff.
One last question?
I mean, in anti-de Sitter, you can take the radius to infinity, and you get Minkowski. Here, you never talk about the radius. Where is the radius?
Oh, the radius I said 1. Because the sitter will never look, global de Sitter will never look like, the global de Sitter will never look like Minkowski. It looks like that.
So you cannot go like
No,
in
but,
anti-de
yeah,
Sitter.
but I cannot take, there's no like a flat limit of DS or IDS. It's not something which is not Minkowski. It's always the same space. Yeah, but I can consider the whole point, which I was doing here. I can make processes in which probe short distances. So that is, I'm not taking that, not the flat limit, but I'm taking really I'm going ultraviolet. And then I can reproduce Minkowski. Because that's the main point of it.
So you say it's a difference between de Sitter and anti-de Sitter.
No, local, I mean, for those, again, I don't know how to, I mentioned before I have a problem with thinking about scattering processes and ideas. I managed to have that problem. Okay, but what I'm saying that, the only thing I was saying that if you take processes which probe very short distance, short invariant distances, then the physics is like in Minkowski space. Yeah.
Okay, so we have to cut it off here so that we get lunch. Just before that, for the afternoon speakers who have not sent the slides yet and you want to use the projector, please send them. And otherwise, please proceed immediately to the lunch break because there's a sharp cutoff. Let's thank them again.